Hello everybody, my name is Tefik. So I have posted some questions on LinkedIn regarding the wall thickness implications on the triaxial state for the stress-based casing design. The one question was should we use the 87.5% wall thickness of the nominal wall thickness in the triaxial design, or are we making the design more conservative? Given that we are already using the 87.5% allowance in the uniaxial burst design, or are they completely different concepts? And then the other question that I put forward was commonly uniaxial design factor of 1.1 is used in conjunction with 1.25 triaxial design factor. So I will try to show the relation between these two. On the second part of the video, I'm gonna basically talk about a macro that I have written for estimating the hydrostatic pressure of the real gas, and then we are gonna put that in our design limit plot that we built in the constructed in a spreadsheet format. So first of all, let's go back to our von Mises yield criterion. So if you remember, we had the tangential stress, radial stress, axial stress, and the tangential stress, and also we had the torsion stress, which we said that we are not rotating the pipe. So for this purpose, we will consider the torsion stress as zero. So we ended up with these three principal stresses, namely tangential, radial, and the axial stresses. So for the von Mises ellipse in the part number 4 video, I recommend you to watch. We basically have transformed this 3-axis state into an ellipse format for the burst side and the collapse side, using all the three main principal stresses. So the first question that I put forward was, well, basically we are accounting for the 87.5% in the uniaxial burst. Should we do it on triaxial, or are they completely different things? So first of all, uniaxial burst or Barlow equation, or API uniaxial burst, we have driven this in the part number 1 of the proof-based stress-based casing design video series. If you remember, it was based on a thin wall assumption, meaning that diameter of the thickness ratio is much greater than 1, and the biggest assumption or biggest disadvantage was it's uniaxial, meaning that we didn't consider any axial stress, or we didn't consider any radial stresses. So we both assumed the axial and the radial stresses being zero. That's why we called it as a uniaxial burst rating. So what we have done is we basically set the tangential stress equal to yield strength. For example, for the purpose of this example, I will take 958 53.5 pounds per foot L80 casing, which is 80,000 psi yield strength, and basically we set we set it to the yield strength, and then we basically solve for the delta P using the thin wall assumption. That's how we came up with that uniaxial burst rating. And then for the subject casing, if we use a 1.1 design factor, and then once we allow the 87% manufacturing for the API allowance, API thickness allowance, then we are ending up with the 7206 psi burst strength. So note that number into some place for now. So the question is, what if we use that wall thickness into the triaxial wall thickness? So triaxial stress state, we know that casing is not in only one stress state at a time. It always under different stress status. So basically in the triaxial we consider radial stress, although being small usually, and then the axial stress, it has a major contribution in most of cases, and then the tangential stress. So principally, the both concepts are completely different. The uniaxial burst is only looking at the tangential stress being equal to yield strength, and then ignoring basically the axial stress and the radial stress. On the other hand, triaxial stress accounts for these three principal stresses. However, in the design limit plot, if you remember our design limit plot, so we had the upper side as the burst, the lower side as the collapse, because it has the positive differential from internal to external on the top, and then negative differential from internal to external on the lower side. If you remember, we had this point over here that basically almost coincides in both stress rating. So why they were coinciding, and then also that question is relevant to the other part where we basically said, okay, a commonly used 1.1 uniaxial design factor is used in conjunction with 1.25 triaxial design factor. I think some companies they don't consider the uniaxial design factor anymore, and then just look at the triaxial design factor for the burst, because we know that the collapse is a completely different phenomena, and then it's based off number of actual specimen tests. So for the burst, this point when the design limit is plotted with the uniaxial burst and the uniaxial burst limit and the triaxial ellipse, sometimes we know that this point coincides. So how does it coincide? Let's look at that one, because it's also relevant to the second part of the question. So in the part number 4 video, I have derived basically the burst side of the ellipse, all right, using basically axial stress plus the backup pressure. For the burst load case, the backup pressure is the outer pressure, external pressure, and then basically I have derived such that you have a solution delta P. So you have the delta P on the y-axis, and then on the x-axis you have the axial stress plus the backup. For the burst load case, the backup is the external, as we mentioned. And here, if we take basically the axial stress plus the external pressure as 0, meaning that I have no axial stress, so the point lies on the y-axis. All right. If you solve this equation, and then if you solve this equation with this assumption that there's no tension or the compression on the pipe, then you will end up with basically delta P, which is the burst rating, is equal to yield strength times 1 to the A, meaning that the ratio of this square, so that's the cross-sectional area, outer area, and the inner area. So you can find the details of this derivation under this part number 4. So I'm not going to go into detail, and then you will end up, if you take, for example, 1.25 triaxial design factor, then you are ending up with 7189 psi. Right? So what we have said in the beginning is, if I take a 1.1 uniaxial design factor and basically 87.5% wall thickness allowance for the uniaxial burst for the Barlow, I'm ending up with the 7206 psi. So as you see, these numbers are very close. That's why in the design limit plot in the softwares, they look like an identical point, but usually, apparently if you build that design limit plot into Excel, this is what we have done on the part number 5. They are not exactly the same point. Why they are not exactly the same point? Because if you remember, the triaxial state considers the radial stress as well. Okay, in this one we basically made an assumption that axial stress is 0. That's the same assumption in the uniaxial burst, and also uniaxial burst was assuming that also the basically the radial stress is 0. in the triaxial state, we know that we are not ignoring radial stress. Although it is small, still there is some amount of radial stress. And plus, in this one, we are not assuming as a thin wall. Thin wall assumption was, what was it? If you remember, DO, diameter over thickness, much greater than 1. Alright, so we are not making that assumption over here. So these two different things basically are causing the values to come very close. If I use 1.25 design factor with no axial stress, if I use the triaxial formula, basically stress state or burst ellipse, okay, and then if I use 1.1 in the Barlow formula, so they are very close, but they are not exactly the same because of the radial stress and the thin wall assumption, right? So if you see the design limit plot, yeah, they will coincide, but they are not the exact same value. So now we answered the first question. The second question is why you use 1.1, and then, you know, in some design manuals, or most of them maybe 1.1, and then you have a 1.25 corresponding triaxial. So this is the answer why why you use 1.1 to 1.25. And also if you think about, okay, so let's forget about the design factors here. Let's say, okay, with the axial stress being 0, this one will be equal to the uniaxial stress. Radial stress, let's forget about it. It's for now, because it's assumed as 0 in the Barlow case. So if you take a wall thickness of 100%, and then if you take a wall thickness of 87.5%, which is the Barlow case, if I use 1.1 design factor in the Barlow, it's a simple ratio from the high school mathematics. So what is it? 187.5% times the triaxial design factor will be equal to 100% times 1.1, and then you are ending up with a 1.25, almost a 1.25. So that's why when companies use some companies may still prefer to use a uniaxial burst design factor. So if they use a 1.1, then they will tend to use a 1.25, because at the 0 tension they will almost coincide in the design limit plot. As I said, they are not an exact value, 71.89 versus 72.06, but for because the line the limits are shown approximately in the design limit plot in some softwares, they will look like an exactly same point. So if we talk about, for example, let's say let's forget about the design factor here. So as you see, there's no API tolerance here, 100%, and then here also there's no design factor. These values, so cross-sectional area square divided to the ratio of, on the denominator you have the outer area square times 3 plus the inner area square, and then to the square root on the top, and then this was the Barlow, if you remember. So that's the 2 times the wall thickness over outer diameter. On both sides you have the yield strength. So if you take these numbers, so you get 89.86 psi with no design factor, and then you get 9059 psi with basically 100% wall thickness on the Barlow. So what I try to say is, yes, at 0 axial stress, your triaxial doesn't almost reduces to the Barlow equation, but because the Barlow equation makes an assumption for the radial stress and the thin wall assumption, the numbers are getting to very close, but not exactly the same numbers, because we know that radial stress is small but still contributing. So before we go to the second page, I think one other thing that I need to talk about. So we say 1 point. So this is, let's assume that this is 1.1 uniaxial design factor for burst, and then this is 1.25 of the triaxial design factor, triaxial state in 100% wall thickness. That's why we set here. So we take the 100%, and then if we use the design factor of 1.25, is almost equal to the 87.5% and 1.1 uniaxial design factor. So what if we use 87.5% in the triaxial state? And that was also the main point in the first question. So we know that on the design limit plot, the cross-sectional area is maybe the ID is pretty accurate because of the drift, but it might be thin on the other side, it might be thick on the other side. The cross-sectional area is pretty much preserved on the joints. So what we can say is the cross-sectional area preserved. That's why you have your compression and the tension limit. They are basically based on the 100% wall thickness, and then it's also same with the axial stress, because that cross-sectional area. Because your tension and compression limit is simply basically your grade of the pipe times the cross-sectional area in pounds. Of course, I'm making this x-axis in pounds. I could put in PSI as well, which I have shown in the part number 5 video. So we know that the collapse part, and then this part, if you remember, that was the impact of the tension on the collapse, based on, I think, 2018 API formula, which is also same as the collapse ellipse that I have driven on the part number 4. This is not basically this is a completely different concept than a triaxial. So the collapse is based on the actual test. So basically you basically take the API regimes and then the DO over thickness ratio. So that's your nominal wall thickness. So the only nominal thickness over here that applies is basically the triaxial burst side. And here, I think 87.5%, if you apply that one, yes, you are basically making that wall thickness smaller. That's why your cross-sectional area on one side gets smaller. And then, of course, when the area gets smaller, force over area, so you are ending up with a higher we call it a higher tangential stress or a radial stress. So I think it makes sense to consider that 87.5% on the over here, because you know that the pipe might be over that 87.5%, but we know that it is there for a reason, and we know that the main point in the triaxial state design or triaxial von Mises yield stress is basically trying to take the advantage of the axial stress in the burst design on top of the uniaxial burst design. Therefore, I don't see any concern of using 87.5% wall thickness in the von Mises ellipse, and plus using a design factor of 1.25. So if you use 1.25 and 87.5%, then this point will not coincide anymore with the uniaxial design limit at 1.5. It will get smaller. So these red snaky shapes are the load cases that I basically just drawn in over there. So yeah, if you wanna refer to the design limit plot, please go back to the previous videos. But overall, yeah, 87.5% wall thickness, I think it should be considered, because it's a pipe. I think it's a irregularity on the pipe in that sense. But comparing with the uniaxial burst is not adding a double conservatism, or it doesn't make it conservative, because yeah, as we mentioned, the uniaxial burst is some companies don't consider it anymore as a limit for that one. Okay, so I think we are good on this page. So basically, let's see if we captured all the questions. Wall thickness accounted. Yes, if we consider 87.5%, I think it makes it complete, because we consider the pipe properties, and then it's completely different. if we ignore the uniaxial burst limit, because uniaxial burst limit doesn't take care into radial stress and axial stress, and axial stress is could have a major contribution. And then the second one is why 1.1 uniaxial design factor was used with 1.25 in commonly in some companies, because if you take 87.5% Barlow and then use it with 1.1, if you take a simple ratio, then you are ending up with a 1.25, so that they are represented on the design limit plot at the same point, crossing point or intersection. It's like two wells crossing each other from above or below, and then at the zero tension or compression. So let's go to the second main thing of the real gas, hydrostatic. So on the part number 5 video, basically I have demonstrated that we could basically build the design limit plot simply on a spreadsheet, and then this in relation with the first page, you could basically put the ellipses to the different wall thicknesses. So you can draw a 100% ellipse with the 1.25, and you can also add another ellipse with 87.5% and 1.25 design factor. So you could see how they overlap with the uniaxial design limit, if you want to see that one. And after these videos, basically I have made derivation for the estimation of the pressure of the real gas using the Abu-Qasim and Dranchik method, and basically I have written a macro about it, a short macro, and in the Excel spreadsheet, so that I could include this macro, and then I could easily calculate the internal pressure profile, basically that originate you remember fractured shoe minus full gas to surface, the burst load case that we considered. I could basically replace the internal pressure using the real gas instead of internal pressure profile estimated using the ideal gas. And basically I have plotted these two in the design limit, which I could show in the second video. So how we write a macro on this one, or how we follow the procedure of this method? First of all, the pressure will be dependent on the gas gravity, the depth. Okay, so you have let's say a depth increment of 500 feet or 1000 feet. All right, so D1 and D2, and then you have the temperature and you have the pressure. So this method over here, just a little bit simplification, I will use the temperature average for the load case, but if you want to make it more accurate, then you could also use the load case temperature profile at each point, which could make it a bit more complicated but probably more accurate. And then I will use the pressure in the originating point. So you will basically first you will estimate the average compressibility factor between D1 and D2, and then you could basically estimate the pressure, because you have the pressure here, and then you will estimate the compressibility factor, and then you will go back to the pressure. So this one I have derived this formula in the hydrostatic pressure estimation. You remember the formula was in exponential format. So the macro structure. So how we do the macro structure? So first we will use a one compressibility factor equal to 1 as an ideal case, like in the part number 5, where I have assumed internal pressure as the ideal gas. All right, and you will use the ideal gas, and then you will of course estimate the critical properties of the critical pressure and the critical temperature. So you will come up with the pseudo reduced temperature and the pressure of the gas. and then you will use the you will estimate the compressibility factor. Then you go to the pressure, all right. And then so once you go to the pressure, what you will do is you will find a midpoint over here, P1 plus P2 divided by 2, all right. And then once you have a new pressure, all right, so you will go to another compressibility factor. And here you could basically you could continue doing the same thing. So you find the Z1 and then calculate another pressure and then find another mid pressure point. So instead of that one, I did basically the first compressibility factor estimation, second compressibility factor estimation. After that, then I go for another pressure estimate, just to decrease the number of loops. Otherwise, it's getting too many loops, right? Overall, I will have four estimate or four number of estimates into the compressibility factor. After using the pressure, then you will calculate another midpoint, and then from another midpoint, of course, you will have this new reduced properties because your pressure change, and then you will do another two loops of the compressibility factor estimation. So at Z number 4, I have pretty much a good estimate because the compressibility factors are getting close, so they are very close to each other. Almost you are in a close to a solution. So the method is basically Newton-Raphson method. So it's basically the previous estimate. You have a derivative here, you have the function here, and then you have the derivative of the function, and then that's how you will get close to the root of the equation. All right. So the fourth step, then I will call it as the compressibility factor final. So if you have a compressibility factor of final, then you are ready to estimate the pressure at this increment point, maybe 500 or 1000 feet above, and then you will continue to the surface. So why this macro makes it easy? Because think about you will have a case. Okay, this was at what, 15,000 feet. Let's say you have almost 30 incremental steps that you need to calculate the pressures each. So you need to have a column 1 of the depths, column 2 of the pressures. And then you have another column with the compressibility factor. Then you should have almost 4 more columns for the compressibility factor iterations. If you have a macro like this, then it will basically do the calculations and the loops in the same cell, which makes it quite practical and quite I think you will save some time. So basically, using a real gas versus a ideal gas, what was the difference in terms of the design limit plot? So you have the design limit plot. If you remember, you have the delta P on the y-axis. So that was internal minus the external pressure. On the x-axis, you have the tension plus the backup pressure. Okay, so this is a burst load case. So the backup pressure is your outside pressure. So that's in pounds. Okay, so what we said is we had a higher pressure estimated with the real gas. So and then we said that it will have twofold effect. One in the delta P, all right, and then the second one on the x-axis. Why? Because our initial cemented profile is same. It's just we changed the way that we calculated the internal pressure profile, and then the ballooning force on top of our cemented profile is basically gonna be higher because you have the 2 times Poisson ratio. You remember, you have the multiplication of the inner area times the internal pressure minus the change in the outer pressure, external pressure times the outer area. So your internal pressure from the initial cemented profile is gonna be higher because your internal pressure calculated with real gas is higher, and thermal force is same because the load case is using the same same temperature profile. So I have plotted this in the spreadsheet, and on the next video I'm gonna show how basically how the load cases differ between the real gas and the ideal gas for the load for the burst load case of frac at Q minus the full gas to surface. So I'm gonna show how it's differing if you just change the method of calculation of the internal pressure. And then on the same video I'm gonna show the different wall thicknesses in the triaxial ellipse, so that we could visualize where each things sit next to each other. Because I mean the softwares that I have used, it's not easy to have a design limit plot with different wall thicknesses or different design factors. You need to go back to another window, change things, and then come back again. In the Excel format, in a spreadsheet format, it's much easier to see everything. To see more curves, more ellipses. Yeah. So that was another thing. So the final tension profile was basically what was it. So we have driven this formula as well. I think it was video number 3. It was the initial tension profile as cemented condition. All right. In the green cement condition, we had the thermal effect. For you remember, for the temperature increase you will induce compression, and then for the temperature reduction you will basically induce some additional tension on that one. And then the ballooning meaning this the one with the Poisson ratio. So yeah, so on the next video we are gonna look at the Excel spreadsheet, and then hopefully that will be beneficial for all of us. Thanks for watching.